Let's take a more detailed look at impulse and the impulse momentum equation. And we introduced it by starting with Newton's second law. That would be the net force equals ma. And we replace the acceleration with its equivalent, change in velocity over change in time. And then you can rearrange this to get force times the time is the change in momentum, or you can put the delta by the velocity. Either way, another useful way to write this is the impulse force times time is mv minus mv initial, so we call that final. And so this is the only equation you need to know. As we go through this, I'm going to ask you some questions, see if you can answer them before I give the answer as we go through. When do we need to use impulse? Usually we can use conservation of momentum. If anything is applying a force to our system, we can bring that object into the system. But if the object applying the force is connected to the Earth, then we'd have to bring the Earth into our system, and it's pretty hard to measure a change in momentum of the Earth, even with a big meteor hitting it. And so that's one time we need to deal with external forces. And so here we have a 1.6 kilogram cart sitting there, and we're going to push it with a 4 Newton force for 0.8 seconds. What is the impulse applied to the cart? And so another symbol for impulse is J, and so it's force times the change in time. And so 4 newtons times 0.8 seconds, 3.2 Newton seconds, the units of impulse. What if they asked you this, though? What is the change in momentum of the cart? Well, you might start calculating and find masses and stuff like that, and after a while you'd realize, oh, wait a minute, impulse is the change in momentum. And so you don't have to do anything. 3.2 Newton seconds is the impulse, and so the change momentum is 3.2 kilogram meter per second. So they are the same thing, they equal each other. Now you might say, wait a minute, Newton seconds, that's not kilogram meter per second. It is. Newton is a kilogram meter per second squared, mass times acceleration. If I multiply that by seconds, I get kilogram meters per second. What would be the final velocity of the cart then? And so the impulse is the change in momentum. Let's write it as mv final minus mv initial. And in this case, the cart is at rest. And so v initial is 0. It's not always 0, though. I could push it after it's already moving, so be careful. Do not leave that part out. And so the final velocity would be the impulse, 3.2, or the change in momentum over the mass, which was given as 1.6 kilograms. So if you look at the units, kilograms cancel, I'm left with meters per second, and it'd be 2. So pretty easy stuff. This is number 3 is a typical multiple choice question. Well, what about this? I'm going to attach a rubber band to the cart and stretch it and let go. What happens to the force on the cart as the cart moves back toward this? And so is it going to increase, decrease, remain constant? If you're not sure, pause and think about it. Here comes the answer. It's going to decrease, because when you stretch the rubber band, if you graph the force versus the distance, it goes up. And so here it's already stretched, and so when I let go, it's going to go back down. And so it decreases. So how do we handle that if we want to calculate the impulse? Well, here's an approximation of what the force distance would look, or force time would look like for this case. And so it starts out at 4 newtons, and as the cart moves along the track, the force decreases to 0. In reality, this would be a curve, but let's just say it's a straight line, make it a little easier. So what would be the impulse now? If you're not sure how to do this, pause it, and then I'm going to go through how to do it. Okay, here we're back. And so you might have said, oh, impulse is the force times the change in time, and the change in time is clearly 0.8 seconds, but what do I use for the force? Not 4 newtons, because it wasn't at 4 newtons for pretty much the whole time. It only started there. That would be overestimating the impulse. It's not 0 newtons. Clearly, there's going to be an impulse applied to the cart. And so how about a compromise? How about the average force? That's one way to do it. And so the average force would be the initial plus the final over 2. I just average 4 and 0 together, and then times the time. And so in this case, we're going to get 1.6 Newton seconds. Another way to think about it is the impulse is the area under the curve, under the force time curve. If you remember, work was the area under a force distance curve. This is force time. This is different, but some of the techniques are similar. And so it'd be the area of this triangle. So 1/2 the base times the height. And so 1/2 0.8 times 4, and I get the same answer. So which is the better way to do it? This is fine if the line is straight. But if it's curved, this is only approximate. Area is always going to work, so you want to know that, and that's the way I recommend doing it. What would be the change in momentum of the cart? Well, hopefully I'm not fooling you now. The impulse is the change in momentum. This is another way to write the impulse momentum equation, and so we already figured out the impulse, so I don't have to do anything to get the change in momentum. 1.6 Newton seconds, 1.6 kilogram meter per second. Impulse is the change in momentum. And finally, what would be the speed of the cart at the end here? And so the impulse is the change in momentum. So I'm just writing different forms of the one equation we're using here. And it did start from rest, and so the initial velocity is 0. And so the final velocity is the impulse, 1.6 over 1.6 kilograms. And so impulse is also change in momentum, kilogram meter per second. So the kilograms go, and I'm left with 1 meter per second. And so very similar to the first example we did, except we came up with a way to handle the changing force. Now, when you actually apply a force to something, there are some limitations to how you can do that. And so I'm going to push a cart with my finger. Which one of these could represent the applied force to the cart? Which would best represent it? And so I'm going to give you the answer here, so pause it and think about it if you're not sure. Here we go. It is D. Why is it D? Because the force is going to start at 0. Right as I first touch it, the force has to be 0. Then it's got to gradually build up to some maximum value. And then maybe I can push steady for a little bit. And then when I decide to stop pushing, it doesn't immediately drop to 0. Time has to go by, and so it drops to 0. In reality, this is probably a curve. Sometimes it drops off steeper than it goes up, but this is the best approximation. You can't start and end without any time going by. This one shows a gradual increase, but then it just ends. And this one shows a gradual decrease, but somehow it started at 4. So this is more of a realistic look at an entire push. So if we did this, what would be the impulse applied? And so definitely pause this and see if you can calculate it. And now I'm going to show you here. Okay, we're back. And so one way to do it is the impulse is the area. And so you break it up into 3 sections. I have a triangle here. And so the area would be 1/2 the base, which is 0.2, times the height, which is 4. And so I get 0.4. So 0.4 Newton seconds of impulse applied for this part. Then I have a rectangle, so that's pretty easy. The base is it 0.6? No, it's just the width of this rectangle, which would be 0.4. So watch out for that. And then the height is 4. So I get 1.6 Newton seconds here. And then finally, this other triangle, you may notice it's the same area as over here, but it's not always, so be careful. So it's 1/2 the base times the height, or 0.4 Newton seconds. So the total impulse then, we can add them all up, and I get 2.4 Newton seconds. You could use the average force idea. The average force here would be 2. It starts at 0, ends up at 4. 2 times 0.2 is also 0.4. The average here is just 4. So 4 times 0.4 is 1.6. The average force here would be 2 again, times 0.2, you get 0.4. So either way is fine. Another way you might see this represented in calculus form is that the impulse is the integral of f dt. And so what does that mean? That just means we're cutting up this into, let's say I had a curve like this. We're breaking it up into slices, and each slice has a width delta t and an average height f. And so the area of one piece would be f delta t. And then I could get all of them and get the area, but that would only be approximate because there's really a curve here. What if I chopped it up in more slices? What about an infinite number of slices? In other words, let delta t go to 0. Now we call delta t dt, and the height would be f. So this is the area of one piece. This thing means add them all up. And so this also is another way to say impulse is the area. We'll get to this later in our course. You don't need to know it for this unit, but you'll see it in the book. And so this is the same impulse curve. What would be the change in momentum? Hopefully this isn't going to fool you. The change in momentum is the impulse again. And so if that's 2.4 Newton seconds, change in momentum is 2.4 kilogram meter per second. So don't fall for that. What a lot of students do is they go to a lot of trouble getting the area, and they get 2.4 for the impulse. And then somebody says, what's the change in momentum? And they think they have to do something to come up with that. And you have to really know the impulse equals the change in momentum. And so what would be the final speed of the cart then? And so see if you can work this out, pause it. Here we go. And so the impulse, again, I'm just writing it different ways. Should be familiar with all the different ways, but this is kind of a useful way to do it. We already figured this out, was 2.4. And so the mass is 1.6 times v final minus 0. Again, the initial velocity was 0. And so v final is 2.4 over 1.6, or 1.5 meters per second. So it's in between the other two cases we got. It's a little more realistic. And if you are a unit freak here, that would be 2.4 kilogram meter per second over kilograms. So we do get meters per second. So if you can do that sequence, getting the impulse, getting the change in momentum, figuring out the final speed, you'll do pretty well on most of these impulse problems. And so try those yourself, do the homework ones, let me know if you have questions.